Do you know plate girders are used to support heavy vertical loads over very long spans in buildings and bridges? Plate girders are used when available rolled eye sections do not have enough moment resistance. In this tutorial, you will learn about design of plate girders as per Eurocode 3 part 1.5 using a practical example. This is part 20 of lecture series on steel design. For other parts, please have a look at link down below. Hey friends, if you're new here, my name is Dr. Qureshi. I'm a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life. In this tutorial, I will go through a practical example on a steel plate girder. The learning outcomes of this tutorial are that by the end of this tutorial, you will be able to understand the design process for plate girders as per Eurocode 3 part 1.5, and you will learn step-by-step process to design a plate girder. This is the problem which I'm going to solve today. It's been taken from a steel designer's manual. We have to design a transversely stiffened plate girder in S275 steel. It is 30-meter long plate girder. It has 2 point loads. These universal beams are applying point loads to this plate girder. Point loads are indicated by capital GK and QK. UDL is indicated by small gk and QK. GK is permanent action. QK is variable action. Step 1 is to work out the design load. We have UDL, GK 25 kilonewton per meter. We have point loads, capital GK 200 kilonewton and small QK UDL 40 kilonewton per meter and point load capital QK 450 kilonewton. And these are the partial factors which I'm going to be using. Gamma G is 1.35, which is a factor for dead load or permanent actions. Gamma Q is 1.5, which is a factor for variable load or live load. And C is 0.925, which we will use in equation 6.10b. Step 2 is to work out the ULS, ultimate limit state combination of actions. And I will be using equation 6.10b of Eurocode 3, which has this C factor applied. Design UDL will be equal to 1.35 into 0.925, which is a C factor. 25 is small gk plus 1.5 into 40. This gives me 91.2 kilonewton per meter. And I apply the same logic to point loads as well, and I get 925 kilonewtons. Once I have got the design loads, then next step is to work out shear force and bending moment diagram. I will not spend too much time in how do we work out shear force and bending moment diagram. Simply here you will have a point load which will be equal to, because we have UDL, and this will be equal to WL over 2 plus P over 2, where P is the total point load. If you apply this, you will get total shear force or reaction at this point. This will slowly come down because you have uniformly distributed load, and it will drop down at point D because you have point load. And in the same way, you will work out this maximum bending moment. It will be worked out by moment due to this reaction subtracted by moment generated due to this point load and moment due to load. In that way, you will get bending moment. I will use this 5-stage process to design this plate girder. And I discussed these steps earlier in part 19 when I was talking about the design process of plate girders. First is initial sizing. Let us see how we can find out initial size of this plate girder. The recommended span to depth ratios for buildings are these, and our plate girder is a simply supported plate girder. Span to depth ratio is between 12 and 20, and I am choosing here span over 15. Our span is 30 meters or 30,000 millimeters. If I divide it by 15, I get 2,000 millimeters or 2 meters of depth of web. If I estimate the flange area, assuming that the thickness of flange will be between 40 and 63, then I will get FYF as 255 from this code BSEN 10025-2. Next slide I will show you. Here we have S275 steel. For thickness greater than 40, less than 63 millimeter, the yield stress comes out to be 255 as we increase the thickness of plates, yield stress is going to reduce. And the reason is that because we have residual stresses, we have geometric imperfections. As we have thick plates, the yield is going to reduce. So you can see that for plates 250 millimeter thick, the yield reduces to 195 Newton per millimeter square. The actual yield is 275 Newton per millimeter square. Most of the time, off-the-shelf market available sections, they are available in less than 16 millimeter thickness. So that's why their yield is not affected. And we normally use table 3.1 in Eurocode 3. But because this is a plated structure, we will be using this table 6 of BSEN 10025-2. Once we have assumed this, we will work out area of the flange. So area of the flange is equal to maximum moment divided by HW FYF. As moment is resisted by flanges only, so moment is equal to force in flanges multiplied by the lever arm. That's how we have found out this formula. So maximum moment, we got it from bending moment diagram. HW is the depth of web, FYF is the yield of flanges. From here, we get this area of flanges. Our plate girder should be able to have this area. So area has to be more than this or equal to this. So for non-composite plate girders, flange width is normally 0.3 to 0.5 of the depth. So if we multiply this 0.3, 0.5, we get 600 to 1000. And our chosen width of flange is 750. And we are choosing the thickness in between 40 and 63, which is 50. So if we multiply 750 with 50, we get 37,500, which is greater than what we have over here. So it has to be greater than required area. Then we have to proportion the web. Now for web proportion, CW over TW should be less than or equal to 124 epsilon. Slender cross sections are allowed as well. Here we are required to design a transversely stiffened plate girder. So we will purposefully choose a web which is class 4. So let's see how we can do it. Now as the limit, TW should be greater than or equal to HW over 124 epsilon. From here, if you put all these values here, HW is 2000 divided by 124, epsilon is 0.92 because we have S275 steel. We get roughly 17 point something millimeters. We have purposefully chosen a thickness which is slightly less than 17. 17 is required for class 3 sections because we have to propose transverse stiffening. And this is the class 3 limit 124 epsilon. Let us classify the section now. So we have flanges 750 by 50 and we have web 2000 by 15. For flange, the thickness of flange is 50. FYF is here. Epsilon is under 235 over FYF. From here, we get this 0.96. Ignoring the weld size for determination of plate width, CF is the width of flat portion of the flange. So here, the entire width is 750. If we subtract thickness of web, which is 15, and if we ignore this weld over here, then we can divide it by 2 to work out this flat portion. So from here, we get 367.5 millimeter. And again, if we divide it by 50, we get CF over TF, which is 7.35. The limit for class 1 flanges is 9 epsilon. So 9 multiplied by epsilon, epsilon is here, we get 8.64. 7.35 is less than 8.64. It means that flanges are class 1. This is the limit for class 1. Let us now classify web. Thickness of web is 15. FYW is 275 Newton per millimeter square. And if we put these values here, we get epsilon 0.92. Again, ignoring the weld, we can get the height of web, which is 2000 millimeters. So CW over TW comes out to be 133. The limit for class 3 web is 124, which comes out to be 114. Our CW over TW is greater than 144. It means that web is class 4. In this 5-stage process, the next step is to dimension web and flanges. Minimum web thickness to avoid serviceability problems like deflection. This is not given in Eurocode 3, so we're using BS 5950 old British codes to work out this minimum web thickness. So for unstiffened webs, it is HW over 250. For transversely stiffened webs, which will be our case, we'll be using these formula. So let us assume that stiffener spacing is greater than HW. The minimum
web thickness to avoid serviceability, it will be equal to HW over 250, which is 8 millimeter. Our thickness of web is 15, which means that minimum web thickness is fine. We also have to check minimum web thickness for ultimate limit stage to avoid compression flange buckling into web, which is also termed as flange-induced web buckling. And this is taken from Eurocode 3 part 1.5, which is for plated structures. Thickness of web should be greater than HW over K FYF over E under root AFC over AW, where AW is area of web, AFC is area of compression flange, HW is height of web, TW is thickness of web, and K depends on utilization of the section in bending. There are various values of K here. This is for class 1, this is class 2, and this is class 3 and above. As our web is class 4, it means that elastic moment capacity will be utilized, so we'll be using this factor. So TW is HW over K. HW is 2000 and K I just showed you 0.55. FYF is 255. E is Young's modulus, which is 210,000 under root AFC is area of flange, 750 into 50. Divided by area of web is 2000 into 15. So we are getting here 4.94. Our chosen thickness 15 is greater than this one, which means that there won't be any flange induced web buckling. After these two stages, the next step is to check bending. And most of the time, the combined bending effect will not be an issue here, because this is an issue when applied shear is more than or equal to 0.5 of the shear capacity of the section. In this case, most of the time you will see that the shear capacity of the section is quite sufficient. So shear will not affect bending. We will not need to work out combined effect of bending and shear. So I will simply check bending. Now bending moment is mainly provided by flanges. And here we have to ensure MED over MCRD. This should be less than or equal to 1. And for class 2 sections, we have this formula. For class 3 section, we have this formula. So for class 1, 2 flanges, but class 4 web, it is assumed that bending is resisted by flanges alone. Bending moment by flanges is equal to force in flanges, which is area times material strength, times the lever arm. The lever arm between two forces is HW plus half of TF here and half of TF here. So two halves will make one whole. So that will be HW plus TF. So area of flange is 750 by 50 and yield is 255 times 2000 is height of web plus thickness of flange is 50. From here we get 1906.03 kilonewton meter. This moment capacity is greater than our applied moment. It means that the section is fine in moment. If the section is not fine in this moment, then we increase the area of flange so that it provides sufficient moment capacity. Once these 4 stages are gone, then we have to check shear buckling of web, and then we will design the stiffeners as well. Now this will be our main topic here. The design of plate girders will be controlled by shear buckling of web, and you will see we will have lots of calculations here. Now how do we check shear buckling? For stocky webs, the failure is by yielding of the material. We have the shear buckling factor using these formula. For slender webs, failure happens due to shear buckling, and here we will be ignoring the effect of shear from flanges. We will just be considering web. Now let us check that if shear buckling is needed or not. So we will be using this formula. Initially our web is unstiffened, but we will stiffen it, so we will use this top formula. The HW over TW is greater than 72 epsilon over nu. Nu is equal to 1. HW is 2000 divided by TW is 15, so that comes out to be 130 something. So that is clearly greater than 66.56. So shear buckling should be checked. It means that we will be using the second formula where failure is going to happen due to shear buckling. Now there are 2 contributions. One is by web, other is by flanges. We will ignore the contribution of flange and simply we will work out the shear contribution by web, where we use this reduction factor approach. And our entire focus now will be to find out this psi W reduction factor. Again, this is the same formula. This reduction factor depends on lambda dash W, the slenderness ratio. And for slenderness ratio, we can use this formula. K tau is shear buckling factor, which you can find out by using formula in slide earlier. Once we have this lambda dash W, we will have a look at this slenderness range. If it is less than 0.8, then we will use the top first row. If it is in between 0.8 and 1.08, we will use the second row. If it is greater than 1.08, we will use third row. And it depends on rigid post and non-rigid. What does mean by rigid and non-rigid? Let's see. A rigid end post has two double-sided stiffeners or a I section attached to the end. On the other hand, a non-rigid end post has got only one double-sided stiffener attached. Let's first of all find out shear resistance of the end panel AB. AB is this panel, and we're assuming that it is a non-rigid end post. We're having quite closer spacing over here. The contribution of flanges will be ignored. So HW is 2000. A is the distance between two transverse stiffeners, which is this distance. It is equal to 1550 millimeter. FYW is 275. VED is applied shear at this point, which is 2293 kilonewton. Web aspect ratio A over HW is A is 1550, HW is 2000, which comes out to be 0.78. So we will be focusing on this panel AB. Web aspect ratio is 0.78. So shear buckling factor, we have these two formula. The 0.78 is less than 1. It means that we will use this second formula. So let us use this second formula to work out shear buckling coefficient. And HW is 2000. A is 1550. If we put all these values, we get this K tau as 12.89. If we put this value of K tau back in this equation, we will be able to get this slenderness ratio, lambda dash W, and that will help us to find out the reduction factor psi. So 2000 divided by 37.4, TW is thickness of web 15, epsilon is under root 235 over Fy, which we worked out 0.92. Under root K tau is the value which we figured out little earlier. This gives us 1.07 lambda dash W. As lambda dash W is 1.07, which falls into these two values, 0.83 and 1.08, and our assumption was non-rigid end post. For key W reduction factor, we will be using the second row and we'll be using this formula 0.83 over gamma dash W. So from here we get EW as 0.77. Once we have this reduction factor, we put it into this VBW-RD to work out the shear resistance of web. So 0.77, FYW is 275, HW 2000, and TW is 15. Under root 3, we get 3681, which is greater than applied shear. It means that shear resistance of web is fine. Let us now work out shear buckling resistance of panel BC, which will not be much different to CD, but we will work out the panel DE separately. The shear resistance of BC is calculated assuming a rigid end post. HW is again same 2000. A is the distance between two transverse stiffeners, which now is 3900. FYW is 275. VED is applied shear, which is this one, 2152 kilonewton. Web aspect ratio is A over HW. This comes out to be 1.95. Now it is greater than 1. So when web aspect ratio is 1.95, it is greater than 1. We will use first formula for shear buckling coefficient, 5.34 plus 4 into HW over A, and from here we get value of K tau as 6.39. Once we have value of K tau, we'll put it back into this equation for lambda dash W, and from here we have everything same, only K tau is different. We get lambda dash W as 1.53. Now again, we will go back here. 1.53 is greater than 1.08, and here we have assumed a rigid end post. It means that we will be using this formula. So the formula TW 1.37 divided by 0.7 plus lambda dash W, it comes from here. And if we put these values, the only variable here is lambda dash W, we get TW as 0.62. If we put this reduction factor value here, again, other values, they remain the same. we get 2932 kilonewton, which is greater than 2152 required for this panel. It means that shear for this panel is absolutely fine. Once shear of this panel is fine, then we are not checking here C and D. It should be fine as well. So now we are focusing on D and E. For panel D and E, you will see that the distance between stiffeners is 5650. FYW is same. VED now is 5154 kilonewton for this panel. And web aspect ratio is 2.83, which is greater than 1. It means that we will be using again the first formula. If we put all these values here, the only thing changing is A, which is 5650. We get 5.84 for K tau. Again, if we put these values back in here for lambda dash W, the only thing changing is K tau. We get lambda dash W as 1.6. So let us see what formula we can use to find out the reduction factor. As lambda dash W is 1.6, which is greater than 1.08, it means that for rigid end post, we will be using again this formula 1.37 divided by 0.7 plus lambda dash W. So from here, we get value of reduction factor TW as 0.6. So when we put this value back in here, we get value of VBW as 2843, which is greater than 515 kilonewton. It means that the shear for this panel is fine as well. Now, once we have checked the shear, the next and most important step is to design web stiffeners. And we normally design these stiffeners same as we will design a compression member or a column. In step 8, the first thing is to find out the width of the stiffener. So HS over TS, where HS is the outstand width, TS is the thickness of the stiffener. It should be less than or equal to 13 epsilons, which is slightly short of 14 epsilon, which is the limit for class 3. This is to avoid torsional buckling. And again, the second formula we'll be using is to find out the minimum IST, the second moment of area for these sections, and this is the effective cross section that we will find. The intermediate stiffeners, they should be designed for PED that arises from shear induced tension field. So if you have this web panel, you saw in theoretical background earlier that it has this tension field, and this will result in some kind of load which is found by PED in any other externally applied load. So if we have a point load, simply we will add this up. And again, this depends on web aspect ratio. This is explanation of different parameters. Here, the key thing to note is sigma XED is the longitudinal direct stress in web. So for symmetric sections, we normally take this as 0. Sigma CRX is elastic critical buckling stress, and elastic shear buckling stress is tau CRX. The buckling resistance of these stiffeners is designed in the same way as conventional compression members or columns, and the buckling length is taken as 0.75 HW, as the stiffeners are fixed between flanges. So that's why it is very close to 0.7 L, which is for fixed supports at both ends. Let us now design a stiffener at A. Now, this stiffener is going to take the bearing force of 2293 because it is directly under the support. So let us assume a single double-sided stiffener with non-rigid end post, and it does not have to be designed for any tensile anchorage force. The double-sided stiffener is assumed to be 280 by 24, where HS is 280, TS is 24. So let us check flange outstands. TS 24 and FY is going to be 265. And that comes from this PSEN 10025-2. From here, you can see for S275 steel, if the thickness is between 16 and 40 millimeter, the yield is going to be 265. So that's where we got this value. HS over TS should be less than 13 epsilon. This is the first thing that we need to ensure. So working out epsilon is 0.94. So HS is 280. This should be less than or equal to 13 epsilon TS. So 13 epsilon 0.94, TS is 24, this is 294. So HS is less than or equal to 294, which means that the torsional buckling is avoided, as is local buckling, since HS over TS is less than 14 epsilon, which is the limit for class 3 compression flange outstand. Let us find out the effective properties. This is web, and we have this stiffener. The stiffener is 24 millimeter and 280 on both sides. So 15 epsilon TW will be equal to 15 times 0.94 0.92 times 15. Again, it gives us 208. So that's where this 208 comes from. These are minimum properties, minimum IST, second moment of areas. If we put this 1.5 into HW, which is 2000 cube into 15 cube divided by A for this panel is, I think, 1550 square. We'll be using this top one as 1550 divided by HW, which is 2000. It comes out to be less than 1. This is certainly less than under root 2. Under root 2 is 1.4. So that's why we're using the top formula. We're getting 16.85 into 10 raised 6 millimeter power 4. Let's now work out the actual properties. The actual properties will be equal to area of the stiffener and the actual second moment of area of this stiffener. So NED, the applied loading over here, is equal to the shear, which is 2293. The area will be equal to not only area of the stiffener, but area of web as well, which is contributing to the entire shear resistance. So first, area of the stiffener itself, so 280 times 24. We have two of these stiffeners, so that's why we multiplied with 2 plus 208 and plus this portion which is 24. So 208 plus 24 times 15, we get this area. And again, we have to work out the second moment of area because these are rectangular sections. So we will be using BD cube over 12. This is the second moment of area for rectangular sections. So first, 24 times 15 plus times 15 is this value. So 15 plus 2 times 280. This will give us the entire height of the stiffener. And there is a cube on this. 24 times these value cube divided by 12. It will give us the I for this section only. And then we have this flat portion where B is 208, the depth is 15. So 208 times 15 cube over 12, we get this 380.28 into 10 raised 6, which is greater than our minimum required 16.85. So this is greater than 16.85 into 10 raised 6 millimeter power 4. It means it is fine. How do we design columns? For column design, first we classify the section, then we work out lambda dash, which is slenderness. If lambda dash is less than 0.2, it means that buckling check is not required. We just check the cross-sectional resistance, and NCRD is AFY over gamma m naught. If lambda dash is more than 0.2, then we check buckling resistance. We check this key reduction factor, and we have this phi as well. We put this value back in here to work out the buckling resistance. So this was the brief process of column design. So web stiffeners are normally designed as compression members of columns. Let us design bearing stiffener at A. The effective properties, we just found out A, and we found out the second moment of area. IS is radius of gyration, which is equal to under root I divided by A. So work out these both values. It comes out to be 149.9 millimeter. Once we have got I, we will work out cross-sectional resistance as well. So cross-section resistance is area times material strength. Area we worked out, Fy is found out to be 265. From here we get 4484 kilonewton, which is greater than applied loading. The applied loading is shear force at that point. It means that cross-sectional resistance is fine. Then we check if buckling resistance check is required or not. For that, we will work out the lambda dash. Lambda dash is equal to lambda over lambda 1. So lambda 1 is equal to this value, pi under root 210,000 divided by 265, we get 88.4. This is lambda 1. LCR is equal to 0.75 HW. So we get this value of LCR. So lambda is equal to LCR over IS. IS is radius of gyration, which we worked out earlier. LCR is this value, which we found out, and lambda 1 is this value, 88.4, which we figured out a little earlier. So this comes out to be 0.11. As this value is less than 0.2, it means that buckling check is not required. Only cross-sectional resistance is required. So earlier we found out cross-sectional resistance, which is NCRD, that is less than applied loading 2293. It means that it is fine. So we don't need to check any buckling here. Let us now move to intermediate transverse stiffness between B and C. So now we are designing these two stiffeners. So for panels BC and CD, for both of them, A is 3900 millimeter. So let us assume double-sided stiffener 80 by 15. HS is 80 and TS is 15. First, let us check flange outstands. Let us check if HS over TS is less than or equal to 13 epsilon. So TS is 15, FY is 275, epsilon 0.92. So HS, which is 80, should be less than or equal to 13 epsilon TS. Epsilon is 0.92, which is 180. So 80 is less than 180. It means that no torsional buckling is happening and no local buckling is happening as well, because HS over TS is less than 14 epsilon, which is the limit for class 3. The effective cross section, it comprises the stiffness plus an effective web width, which is equal to 15 epsilon TW. So 15 epsilon TW, we get 208 from both sides, and this is the horizontal one is web. The vertical ones over here, these are the stiffeners. Let us check the minimum stiffness. So A over HW is the web panel ratio, which is 1.95. That is greater than under root 2. When it is greater than under root 2, we will use these minimum properties. Minimum second moment of area is 0.75. HW is 2000. TW is 15. From here, we get 5.06 10 raised 6 millimeter power 4. Actual IST, or second moment of area of the transverse stiffener, comes from here. So first we have the stiffener. So we have B is equal to 15. D is this entire depth, which will be 2 times 80, plus in between we have this 15. So that is D cube over 12. So this is for the stiffener, and the web portion, we have B will be equal to 208 plus 208 plus, so 208 and 208, we add it up times the depth is 15, so 15 cube over 12, we get 6.82, which is greater than the minimum required. It means that it is fine. The effective stiffener cross section should resist a compressive axial force PED arising from shear induced tension field plus any other applied load. Here we don't have any other applied point load, so simply we'll be using these two formula. As A is greater than HW, so I think we'll be using the first formula. Double-sided intermediate stiffeners are designed to resist a compressive axial force PED. Here A is greater than HW. Sigma X ED is this value. For symmetric sections, it is 0. It means that this entire portion is going to be equal to 1. VED is applied shear, which comes from here, which is 2152 kilonewton. We have to replace these values here. Now, first we have to find out tau CR. For tau CR, we have K tau into sigma E. Sigma E, we use this formula, and there is a direct formula over here. We simply add thickness, and B is actually the height of the web. When we add this value, we get sigma E as 10.7 Newton per millimeter square. As A over HW is greater than 1, so we'll use this first formula for shear buckling factor. And here HW is 2000, A is 3900. From here, K tau is 6.39. When we have this K tau, we put it back into this equation. Tau CR is equal to K tau into sigma E. K tau is 6.39. Sigma E we just found out from here, and this gives us tau CR 68.2. If we put all these values, VED is applied shear, which you saw a little earlier. 0.8 comes from the formula. Tau CR is this value 68.2 into HW is height of web, which is 2000. TW is thickness of web. This gives us 514 kilonewton. So our stiffener has to be designed for this load. Effective properties. Now, how do we find out effective properties? We found out IST little earlier, so there's no need to repeat it. I will find out the area of this portion. So area will be 2 into 80 into 15, which is area of these web stiffeners, plus the portion of the web which is attached here. So 2 into it is this portion. So area of this entire web will be 208 plus 15. That is the width, and the height is 15. So from here we get 8865 millimeter square. If we put value of I and A into this equation, we get IS, which is radius of gyration. This comes out to be 27.7 millimeter. It will help us find out the slenderness ratio. Cross-sectional resistance is AFY over gamma M naught. A we found out, FY is 275. This comes out to be 2438, which is greater than applied load PED 214 kilonewton. Now we have to check the buckling resistance. So shear buckling formula, lambda dash is equal to lambda over lambda 1, where lambda is equal to LCR over IS. IS is radius of gyration, which we found out a little earlier. LCR is 0.75 HW, which is 1500. Lambda 1 is simply pi under root E over FY. E is Young's modulus. So from here we get 86.8. If we put all these values here, we get lambda dash as 0.62. As this is greater than 0.2, this means that buckling check is required. Now for stiffeners, we only use curve C. So for curve C, the imperfection factor lambda is equal to 0.49. This is from this clause BSEN 1993-15, clause 9.42. And here we will put all these values into this phi formula, where alpha is 0.49, which we found out earlier. Lambda dash is 0.62. If we put all these values, we get value of phi. Now phi has to be used in this reduction factor formula key. So phi is equal to 1 over phi plus under root phi square minus lambda dash square. We put all these values, I'm getting 0.77, which is the reduction factor. Now NBRD will be equal to reduction factor times AFY over reduction factor is missing here, so we need to add this reduction factor times AFY over 1. If we put all these values, you can see that I've got NBRD as 1881 kilonewton, which is greater than applied load that we worked out. It means that the stiffener is fine. Now, stiffeners at B, C, and CD, they have to be designed in the same way. Now, I will design a stiffener at D. This stiffener is taking not only the load from tension field, it is also taking load from this universal beams, which is 925 kilonewton. Let us try the same 80 by 15 stiffeners, and the minimum stiffness requirements are same as before. For panel DE, we have A5650 millimeter. Now, A is greater than HW, so compressive axial force is given by this formula, where sigma x ED is 0 for symmetric sections. It means that this portion is going to be 0, and that means that this entire portion will be equal to 1. And VED is applied loading, which is 1440 kilonewton. In the same way, I will find out tau CR. Sigma E is same as before, and K tau, because A has changed, so let us see there is a difference in value or not. So K tau comes out to be 5.84. Tau CR is K tau into sigma E. Sigma E comes from here, K tau comes from here. If we put all these values, we get tau CR as 62.4 Newton per millimeter square. If I put all these values, VED 1440.8, tau CR we found out earlier, HW 2000, TW is 15. I am getting 57.6 kilonewton, but this is negative, so it cannot be a negative value. That means that the compressive force due to tension field will be equal to 0. Now the total compressive force to be resisted is equal to load that is applied from universal beams as point load on plate girder, which was 925 kilonewton plus 0. So this is giving me 925 kilonewton. The buckling resistance of the stiffener, as above for panels B and C, it was 1881 kilonewton. That is greater than 925. It means that the buckling resistance of this stiffener at D is fine. Now, once we have designed all the stiffeners, this is giving us the full picture. Now, details of these stiffeners are here. We have these outside stiffeners, which is two stiffeners 280 by 24, and these two stiffeners are at the supports. And then we have these intermediate stiffeners, including this central stiffener, which is two stiffeners 80 by 15. And the flange width is 750. The total height of the section is 2.1 meter, and thickness of web is 15, and thickness of flange is 50. So this gives us the overall dimensions of the plate girder after going through all the design process.